Hello everybody, my name is Andreas. I am currently pursuing a master's degree at the University of Constance, and today I want to show you some of the things that we've been working at our chair. So the work we want to present to you includes several parts consisting of simulation models for the domain name system, for multicast DNS, and DNS service discovery. Daniel Kaiser, who is also sitting there, has been working on enhancing the privacy of users with respect to mDNS for a while now. Since our topics are closely related, we decided to create simulation models for DNS and mDNS in order to evaluate the concepts that we have developed at our chair. Hence, we also have simulation models for privacy-enhanced mDNS and for stateless DNS. With our DNS model, you can design networks using DNS and resolve resources. You can also use it to create new extensions to the domain name system. For instance, you could develop new resource record types and use our model as a basis in order to validate that the resource record types do what you expect them to do. mDNS can be used in addition to what you would use otherwise, or even as a use case for your own protocol. For instance, if you were to develop a new multicast transport protocol using OMNeT++ and the INET framework, you could use our model on top of the protocol in order to evaluate the performance. So the privacy extension and stateless DNS are experimental and were developed at our chair. You can combine them with other protocols as we've done it with mDNS, or you could just see how they work and see if they may provide a solution to a problem you've been trying to solve all along. Now, we only want to provide you with a high-level overview of what our models can do and what you can do with our models, and do not want to go into detail about every component that is implemented for our model. Here you can see different components which you would actually use, which are all simple modules. So there are, of course, other components which are used by these modules, such as caches and configurators. We also defined a special packet, a DNS packet, which has fields and arrays specific to DNS packets. Packet sizes are calculated using name compression, and with our serializer implementation, you can also create PCAP traces where name compression is also applied. Now, the DNS server base provides a functionality you wouldn't want to re-implement for every other DNS server. In this case, it's the part of iterative resolving, which is used to resolve resources by going along the DNS hierarchy until you obtain your final answer. The DNS auth server is a name server that is authoritative for a domain. For this, you can define zone configurations. The DNS caching server, on the other hand, is not authoritative for a domain and only resolves resources. However, in doing so, it also caches the responses it receives, and future responses will also be based on records in the cache. The DNS echo server is a stateless DNS server which provides the basic functionality you would need in order to use stateless DNS. The client can create queries and send them to DNS servers, which are specified in the net description. These DNS servers are known to you as the primary and the secondary DNS server, which you can, for example, define on your desktop computer or in a router. Now, the client also provides, or if provided with a callback handle, the client will call the function when the resource has been resolved, such that you can use it in order to perform some operation on the answer. So this is actually what you would need in order to resolve resources within the end hosts. And to make it easier for developers already familiar with DNS bind servers, we decided to support zone configurations using the bind syntax. The config has to be placed in a text file and then passed as a parameter in the net description, for instance, to the authoritative server. Here you can see the pan-RSZ name server for the University of Constance with a couple of resource records. For instance, a CNAME record pointing to an IP address record. Now, CNAME chaining is also one of the functionality that is already provided within our simulation model. However, there are also records such as mail records, which, although they are properly initialized within the zone configuration, do not have currently any logic to resolve them properly. So this also brings us to the capabilities of the DNS simulation model, with which you can already design networks using DNS and map the hierarchical structures you know from real-world systems. For this, of course, you need the recursive and iterative resolving, which is supported by our DNS server-based implementation. Now, as you've seen, we do not support all resource record types. Current types that are supported are A, quadruple A, NS, pointer, service, CNAME, and text records. For other records, for instance, in the authoritative server that has to resolve resources, we have placeholders where you would have to implement the logic for a particular resource record type. And as previously mentioned, we support name compression, which is used in DNS in order to reduce the packet sizes. Now, current limitations include that you have to design your DNS networks manually and cannot use some sort of dynamic configurator. This means you have to define all zone files manually, you have to link parameters and specify IP addresses. We also have rather simple cache implementations and do not support more sophisticated rules like the bailiwick rules, which were used as an answer to DNS cache poisoning attacks. You can also, we do not support dynamic zone updates, which are used to change resource records for a server remotely, which then also have to be synchronized with other servers. And we do not support DNS tags, since this would have added a whole new dimension of complexity to our simulation. Now, we found that mapping the DNS system to INET with respect to being extensible and RST compliant and all that was one of the greater challenges. There are, of course, resolver implementations that fit into only one file, but we do not think that they are really reusable. And one design goal from our side was that our simulation model can be used by by many people, by many users. Now, also, for instance, for the caching parts, there are no specifications within the RST, and just we needed to decide what functionality from real-world implementations actually to implement within our simulation model, since this already differs between different implementations. So that's a part for the DNS simulation model. Now we also want to show you how our mDNS simulation model is structured. So here you can see we have less simple modules, mainly the mDNS resolver and the mDNS network configurator. These are the high-level components that you would actually use. The mDNS resolver provides the actual functionality you're used to have from the Avahi daemon or the Bonjour service. It is RFC compliant and based on the Avahi implementation, from which we also try to imitate the architecture in order to make it easier for developers to start developing extensions using our mDNS model. As you can see, the resolver also uses other components which are not simple modules, but rather abstractions of common functionality an DNS resolver should have. For instance, the announcer takes care of announcing resource records to the network. For this, it schedules the resource records using the schedulers. It also handles conflicts and takes care of graceful leavings. For instance, if a shutdown has been initiated. Now, the schedulers are split into 3 different parts, one for scheduling probes, one for responses, and one for queries. This makes sense not only because there are different delays involved, but also there's some different logic to all these schedulers for scheduling different types. So this architecture is actually taken directly from Avahi, and we believe it makes extension a lot easier. Now, as you can see, there's also the simple module, the mDNS network configurator. As you can see here, basically, you just place it within your network, as you would do with the IPv4 network configurator, and then it will automatically configure mDNS resolvers based on the parameters you have provided. This took quite some consideration from our side, since from the start we wanted to perform larger scale simulations using this model. And now we don't have to configure each node individually and by hand. Now, this also brings me to the capabilities. As I've previously mentioned, the mDNS resolver is RFC compliant. This means we support mechanisms such as known answer suppression, duplicate question and answer suppression. We also respect the different scheduling guidelines which are specified within the RFC. What is currently not implemented are, for instance, in Avahi, there's shared resource records and unique resource records are distinguished. They have distinct data structures. This is not done in our implementation, and the implementer has to make sure that he or she doesn't misuse the different resource records. Now, with mDNS, which is often used in a combination with DNS service discovery, you often have an application that goes online at some point and then uses inter-process communication to announce itself via mDNS. From this paradigm is currently not supported, since we do not make use of the internal message passing system at the moment. We have defined message kinds such as send query or announce service, but and we also have placeholders, but we haven't implemented this yet, so you cannot just plug our resolver into a compound module and communicate from another module that you want to announce the service. As for the challenges, this is similar as for the DNS model, deciding what functionality actually to implement. Different real-world implementations provide different functionalities. Also, the dynamic generation was quite difficult because we also support the dynamic generation of mDNS networks with the privacy extension, such that we have to set links between nodes and decide which nodes want to share data with each other and want to exclude other nodes. So we have used our simulation model for an initial analysis. We want to find out how strongly traffic is reduced during the announcement phase when the privacy extension is also used. I do not want to go into detail about this plot, and rather just want to say that even though the creation of our models took a lot of effort, now that we have them, these kind of analyses with different parameter settings are now much easier than with experimental setups. As for stateless DNS, we haven't done any analysis yet. Daniel Kaiser will perform more detailed analysis with the privacy extension and stateless DNS. The focus of my work is more on mDNS itself and multicast traffic in general. And I guess the basic message here is that you can use our model as a basis in order to work with DNS and mDNS and create new extensions to the protocol more easily. That's also why we want to tell you how you could use our models. For instance, if you wanted to create a new DNS caching strategy, then you would have to implement our DNS cache interface. For this, you would have to initialize your DNS cache within the server or client, depends on what you want to use. But the server, for instance, already has the necessary cache calls, such as lookups, insertions, and deletions in place, and thus you would only have to implement your cache and change a few lines of code. On the other hand, if you wanted to implement a new DNS server which also has to support iterative resolving, as I've seen before, then you could just extend our DNS server base, which provides the API method handle query, which returns a DNS packet. Now, if a DNS packet is received, the implementation has resolved the resource, and a response can be sent to the courier. If the DNS server base instead gets a null pointer, then it expects that the resource couldn't be resolved, and if recursion is available, then iterative resolving has been initiated by contacting a root server. The server base will then set some identifiers in order to remember the query and later be able to send the final answer to the original courier. So that's it from what we wanted to show you about our models, and now we want to also look at some perspectives about the future of our model. Well, okay, the last slide doesn't even matter anyway. Well, originally I want to talk about what I'm working on right now and various possibilities for the future, but after talking to some people here on the summit, I've realized that the DNS simulation model is probably the most interesting to many people, and thus I wanted to encourage a discussion of how we could integrate the DNS simulation model within INET such that it can automatically be used when you create, for instance, an internet simulation. So this is it from my side. Now I'm looking forward to hearing some interesting questions.
Thank you. So, comments. Does everyone feel equipped to integrate this with their simulations? Who's using DNS in their simulations? Anyone doing internet level simulations? Not so much? Let me ask you this then. You said right now you don't do dynamic updates, right?
Yeah.
What do you think would it take to bring this back or actually integrate this for the first time into that model? To also be able to play around maybe with attacks against the DNS system?
Well,
is this something that is
feasible?
Because it was on your bullet point list.
Yeah.
Right? So I thought,
I believe it is feasible, and it is it's actually more or less unique to the authoritative servers that actually do have zones, and thus I would probably implement it at the authoritative server side and add a new message type. Well, it's difficult. I think this needs a lot more consideration. So from the architectural point of view, it is completely no problem, but you have to be RC compliant in order to make it realistic. So when you have dynamic zone updates in your simulation, and yeah, and you want to use it to analyze problems such as attacks and so on, it has to be, well, almost like real-world implementations would actually do it. And maybe you would also need multiple different implementations for this, I don't know, in order to have a good overview of how you can protect yourself from attacks.
But it sounds like a feasible basis for it, if it is kept modular enough, which it certainly looked like.
Yeah, I guess an even bigger problem would be to integrate it with INET. For instance, now name resolution is done automatically and instantaneously, and DNS is not something where you get your answers instantaneously. So everybody in their simulations would have to wait for the answer, and I don't think this is that easy to implement. So
are you looking for adoption into INET? Would INET be interested in adopting this? Possibly. Okay. Anyone else have a question? Otherwise we move to the next. Okay, then we move to the next stuff. I'm very silly.